Okay. Hi, everyone. I'm Savita Mathur. I'm working at the Instituto de Astrofísica de Canarias in Tenerife. And today I'm going to talk to you about the work that I've been doing on the study of stellar structure and dynamics, in particular using astroseismology. So my research interests are divided into two. First, stellar structure and evolution by applying astroseismology, mostly data analysis and stellar modeling, as you will see. And on the other hand, I'm also studying stellar rotation and magnetic activity using modulation in the photometric data and as well astroseismology. So I'm just pointing out that this HR diagram, the stars I will focus on. So low mass main sequence stars, subgiants up to the red giant branch. So on the stellar structure part, I have this pipeline, A to Z pipeline, which allows that I've developed to measure global seismic parameters for solar-like stars where solar-like oscillations are excited through the turbulence in the outer layers of the stars, creating these acoustic modes that we study. So here on the left, you have power spectrum density as a function of the frequency for the sun. And while you have different variabilities, I can say in this power spectrum, we will focus here on the acoustic modes. We have this nice bump here. And one easy quantity that we can measure just by looking at this is the frequency of maximum power, nu max, which is related to the surface gravity of the star. Then if you zoom on to the modes, which are on the right here, you can see that there's this repeated pattern where you have the L equals 3, 1, 2, 0, 3, 1, 2, 0. And this allows us to define the quantity that we call the large frequency separation, delta nu, which is the difference between two modes of same degree and consecutive order. Just like the octave of a piano. And this quantity is proportional to the square root of the density, mean density of the star. So by combining these two global seismic parameters with a good estimation of the effective temperature and using seismic scaling relations based on the sun, we can have a first good estimation of the radius and the mass of the star with a pretty good uncertainty of 5 to 10%. And these relations have been tested both theoretically and observationally, and they have the power of being model dependent. And if we have access to the individual frequencies of the modes for the high signal to noise ratio stars, then we can do further modeling by using this extra information. This has been done on a large sample of stars, showing that we improve the precision on the mass, radius, and age. So here on the right, you can see this plot showing an example of a star observed by Corot, where Labrador and Goupil showed by how the determination of the age of the star improved when we were using more and more seismic information. So here we're using global seismic parameters, and then we were adding little by little individual frequencies. So of course, this is all model dependent, but when we do this, we also have access to the structure of the star, like the base of the convection zone. So let me move on to one of my recent works, which is on studying solar-like oscillations in the Kepler data. While the mission stopped a few years ago, it still contains a gold mine of data where we can do astroseismology. And this was triggered by the fact that in 2017, NASA realized that there was some issue in the way they were processing the short cadence data, the 1 minute data, that led to higher noise for some of the light curves. And here you have an example of one of these stars where you have in black the DR25 data and the DR24 in black and the DR25 in red, the new data. And you can see how the bump of the oscillation appears better with the new data release. So from there, We studied a sample of 2,000 stars observed for 1 month during the first year of the Kepler mission. And here on the right, you have a modified HR diagram where you have the delta nu as a function of effective temperature. And in gray, you have the stars for which oscillations were detected in 2011. And in red, you have 99 stars for which we detected solar oscillations using the DR25, so new detections. We notice that these stars are actually fainter with lower mode amplitudes. You can also see that they are in general also massive and subgiants. So we measured the delta nu max of the stars. We had effective temperature, many of them from spectroscopic observations. And by combining them, got radii from seismic scaling relations. And here we can see the comparison of the seismic radius with the Gaia radius. And you can see that there's a pretty good agreement, close to the 1-to-1 line. Here you have the ratio. While you can see that there seems to be a little trend, they agree within 20%, but there is a little trend with the evolutionary state of the star. In addition to this, I've been working on analyzing K2 data, where we had new detection of solar-like oscillations for 60 stars, also all the red giants observed during all the campaigns of K2. And now I'm also working on test data. And all of this has an application either for galactic archaeology or the characterization of exoplanetary system. So this second part of my work is to study stellar dynamics with the stellar surface rotation, magnetic activity, but also study the impact of the activity on astroseismology, and finally look for stellar magnetic activity cycles. Here you can see the nice butterfly diagram for the sun with the 11-year cycle. And here on the right, you have the cycle period as a function of the rotation periods based on stars observed by the Mount Wilson. And you can see how the sun seems in between these two branches that were defined by Bohm-Wittensen. So it seems that the sun is peculiar. So by studying stellar magnetic activity cycles, it's interesting to make this solar-stellar link in order to understand the evolution of the dynamics of the sun in the future. So to study rotation from Kepler-like data, photometric data, we can use periodogram, time frequency analysis, autocorrelation function. We have also recently implemented a machine learning tool, the Rooster, which is using random forest algorithm. And since we are measuring these rotation periods due to active regions that are present on the surface of the stars, we can measure a proxy of the magnetic activity, which we call the SPH, which is the standard deviation of the time series based on subseries of 5 times the rotation period of the star, so that we are sure that we are measuring activity related to active regions. That's one part. The other thing is that there is impact of magnetic activity on astroseismology. We know for the sun that when the magnetic activity increases, frequencies increase, and the amplitudes of the mode decrease. So there's an anti-correlation, which has been seen then in many other stars observed by Corot or Kepler. So magnetic activity affects the detection of acoustic modes. And actually, looking back at the stars observed during the survey phase of the Kepler mission, we can see that many of the stars where we hadn't detected oscillations were maybe too active. So here you have the SPH as a function of the rotation period. In red, you had stars where we had detected modes, and in black, stars where we didn't detect mode. And actually, only 32% of the stars where we didn't detect modes have a magnetic activity level above the level of the sun at maximum activity, which means that there are other reasons why we're not detecting the modes for the stars with a low SPH value, which can be metallicity, inclination angle, binarity, and we need more follow-up observation in order to confirm what's the reason for this non-detection. And then the last part of the work that we've been doing with people in my group is the study of the surface radiation magnetic activity for all the Kepler stars, main sequence and subgiants. These were a sample of 160,000 targets observed for 4 years by the mission. And we, by applying our pipeline and the machine learning, we finally detected reliable rotation periods for more than 55,000 stars, which makes it the largest catalog of rotation periods with Kepler. And here you have the rotation period as a function of the effective temperature for the main sequence stars and for the subgiants. You can see how for the subgiants we now have these nice slow rotators that were not present in previous catalogs. So this is the reason why I put up this project, to use this gold mine of stars with detected rotation periods, which means also active stars, to look for cycles in these stars, but more in an automated way, since we have so many stars. So using machine learning or whatever other techniques we can use. So I think I will stop here. And if you have any questions, you can send me an email to this address. And thank you. Bye.